Okay, so today I wanted you to do a weighted average problem. So we'll take a look at actual percent abundances of elements or isotopes of a particular element. And once we're done with that, we will actually then start to talk about our modern theory and what we now believe is true after Bohr. So first problem that we'll do is that carbon has 3 isotopes. And the 3 isotopes are carbon-12, so C12 is 98.5% abundance. So this is like with the bean activity, if there were only 3 different types of beans, and one of the beans, you had 98.5% of all the beans were this type. Carbon-13 is 1.02% abundant, and the rest is carbon-14. So a couple things that I'm assessing right here is, do you know isotope symbols? Do you know how to use the weighted average formula? And of course, when you're dealing with percent abundances, do you know that all the percent abundances have to add up to 100%? So that's the key here. So we know carbon-12. If I want to find the average mass, that's going to be mass number 1 times the percent abundance of mass 1 plus mass of the second mass times the percent abundance of mass 2. So let's find the percent abundance of carbon-14. So we do 100 minus the sum of 98.5 and 1.02. And with that, we get 99.52. So we get 0.48% abundance for carbon-14. So with that, now we just have to plug those values into the average atomic mass formula or the weighted average. So we have our average mass equals 12 because that's the mass of carbon-12. Now, to be honest, the mass of carbon-12 is not quite 12. It's a little bit different than that, but for the purposes in Chem 1, it is good enough for us. We don't need to get that precise with it because it's not that important. So what I'm saying is the values we're actually getting are different than the average masses on the pure-act table, but that's because I'm simplifying the calculator pushes for you. So we have 12 times 0.985, the percent abundance as a decimal, plus 13 times, be careful, 1.02% as a decimal is 0.0102. And then 14, be careful again, some people see that 0.48 and they want to plug 0.48 in here. But to get from a percent to a decimal, you divide by 100, or as you've probably heard in math, move the decimal 2 spots to the left. So if I do this, the average mass is 12.0198 AMU. And that's pretty close to the actual value on the pure-act table, which is 12.011, I believe. So very close. It's close enough for us to understand that. So a couple things. Take a look that our average is between the minimum mass, 12, and the maximum mass, 14, and that the average is very, very close to 12 because we have a significantly, most of the carbon isotope is a mass of 12. So the average is going to be closer to a mass of 12. So that would be how to calculate a weighted average for an actual element. Okay. Moving on then, we have talked about the history of the atom from Democritus all the way through Bohr and seen how the complexity of our knowledge of the atom has grown or changed throughout and gotten more and more complex. So we're going to pick up with Bohr and talk about the things he did, and that Bohr talked about energy levels and orbitals, and he was very right on some things and very wrong on others. So we just have to take a look at how we can now know what's happening versus what Bohr said. So Bohr was right that he talked about energy levels. So Bohr was correct that electrons are certain distances from the nucleus. They have certain energies. So energy level, definition, is a distance from the nucleus. Again, we're going just some basic definitions here, good enough for Chemistry 1 explanations. So when you talk about an energy level, we're talking about the distance from the nucleus. Now, Bohr said that the electrons orbited the nucleus like planets around the sun, which made sense. It fit another theory about the universe or solar system, but he was wrong with that. Terribly wrong. That's okay. We'll give him a pass on that. But we do still use his terminology of an orbital. Instead of an orbital being like two-dimensional, just orbiting like in an elliptical pattern, an orbital is just any pathway about the nucleus or around the nucleus. So it's a pathway around the nucleus. So these are two terms you definitely need to know, energy level and orbital. So what we're going to focus on now is the orbitals. What are these orbitals? What are these pathways around the nucleus that these electrons can take? Well, one thing you need to understand is that since all electrons are negatively charged, they're going to want to repel each other. So we can only fit so many electrons in one particular orbital. So there's a maximum of 2 electrons per orbital, meaning in any one specific pathway we can have 0, 1, or 2 electrons. That's it. Now some of the orbitals look very similar, so it gets confusing saying, wait a second, can you fit 2 or 6 in there? 2 electrons per any one pathway. And we're going to start taking a look at what those pathways are. I will describe them. I will do my best to draw, but I'm a terrible artist, so when I come back, you will see actual 3D models of these orbitals, and that will give you a much better idea of what they look like. They're pretty complicated. At least they get pretty complicated. So the first type of orbital is called an s orbital. I like to think, and I don't know if this is true, but I like to think that the S stands for sphere, because s orbitals are spherical in shape. They are spherical in shape. So there's only one way that you can have a sphere around a nucleus, because if you twist it, turn it, anything else, it's going to look identical. So when you're looking at s orbitals, there are exactly one s orbital per energy level. So as I said, the terminology is very important. I use both major terms here, orbital and energy level. So there's one spherical shape around the nucleus for every distance from the nucleus. Because remember, the electrons can only exist at certain distances from the nucleus. So think of this sort of like Russian nesting dolls, where you open up one doll, there's a smaller doll inside. There's another, and then you open up that one, there's a smaller doll inside. That's kind of like what it is with these s orbitals, only you won't really call them inside. There's a small sphere that's at the first energy level, closest to the nucleus. Then around that one, there's going to be a slightly larger sphere, which would be at a second energy level, and then another larger sphere. So there's going to be multiple spheres, but they're going to have different radii. So you can think of like a ping pong ball inside of a baseball, inside of a softball, inside of a soccer ball. And each of those spheres is a certain distance from the nucleus being the center of all those. So that would be an energy level, but they all have the same general shape, or orbital. So there's one s orbital per energy level. Now, since we just found out that there's 2 electrons maximum per orbital, if there's only one s electron per orbital, there are 2 s electrons maximum per energy level. So in any one of those spheres that I was talking about, like the ping pong ball, there could be 2 electrons in that. Then you get the baseball around that, there'd be another 2 electrons maximum in that one. So I can get more s electrons, but they have to get further and further from the nucleus. So there are 2 s electrons maximum per energy level. And we'll talk about the number of different energy levels as we go through. So we've got that. I'll start on a new one. I'll do it on here. Why not? Just a different color. The next one would be a p orbital. I'm not sure why they call it a p orbital, like I said, but I come up with little names that help me remember the shape with the name of the orbital. So p orbital is going to be a little bit more complicated. So it is a peanut shape. So it sort of looks like that with this artist's rendition. So it sort of looks like a peanut. Now, just like Chemistry 1 might be one of your more complicated or complex classes, if you want to do just as well in chemistry as you say in a class that's easier for you, you'd have to put more energy into this more complex class. Well, same thing with the orbitals. A p orbital is definitely a more complicated shape than a spherical orbital. So p orbitals just naturally means that the electrons in a p orbital have more energy. And what we're going to with this is everything's about energy you're going to find. This is a recurring theme over and over and over again this year, is that nature prefers things in low energy states. So we will continue to talk about that. And here's our first opportunity to discuss that. So when we're talking about the energy of electrons, it's about the complexity of the shape and how far away they are. We could run a 100-meter dash, or we can run a 200-meter dash. If they're both straight, equal complexity, but one is farther away, so that takes more energy. Same thing with energy levels. The farther away, the more energy those electrons have. Anyway, back to p orbitals. So they're peanut shaped. So you could take a peanut, imagine a peanut or a circus peanut. Sometimes those are good, sometimes those are nasty, depending upon your feelings of circus peanuts. But you could take a circus peanut and you could actually rotate that and it would look differently to you in three-dimensional space. So there's actually going to be more than one p orbital. Now, it turns out the way that they were discovered in an atom to exist is all along the three-dimensional axis. So they're all going to be perpendicular to each other. So we have one that's vertical, straight up and down. We have one horizontal that's sort of sideways to the board, and then this is the one that's hard to do. You have one that's sort of like going in and out of the board, which you draw at an angle to. So because there are three different axes in three dimensions, like in our three-dimensional world, there are three different p orbitals per energy level. So there are three p orbitals per energy level. But let's take a look. We know from before that any one singular orbital can have a maximum of 2 electrons in here. So if we take a look at this orbital that is vertical, we could have an electron in each lobe, if you will. They don't have to stay in the different lobes of that, but this could have 2 electrons. This orbital could have 2 electrons, and this orbital could have 2 electrons. So because we have 3 different, distinctly different p orbitals in each energy level, we can have 2, 4, 6 electrons, or p electrons. So there are 6 p electrons max per energy level, or per distance from the nucleus. Again, every time I say the word orbital, you need to be thinking pathway, different shape around the nucleus. Every time I say energy level, you need to be thinking distance from the nucleus. Again, think about the ping pong ball, the baseball, softball, soccer ball. Think about that nesting about energy levels. I think that'll help you out. So these are 2 of the most basic types of energy levels, but you can see from the S to the P's, things got more complicated. Well, we have 2 other different types of orbitals that we're going to take a look at. One is the next one's the d orbital. So d orbital, I like to call a double peanut, because it's like 2 peanut orbitals that have the same middle. So this is a double peanut. And it looks sort of like that. We have a peanut this way and a peanut that way, if you will. That's how I like to think of it. Whatever. They don't line up on the axes. They actually line up in the space on the axes. And they can get a little bit more complicated as well, but we're sticking with the generalities. Well, if you started to see a pattern going back to the previous slide, it's a really short pattern, so it's easy, see a whole bunch. But there's 1 s orbital per energy level, 3 p orbitals per energy level. It turns out that there are then 5 d orbitals per energy level. So there are 5 different ways to make that double peanut shape. So each of those double peanut shapes can house a maximum, again, because that one shape I'm drawing is 1 orbital. It's getting more complicated. It's more energetic. Each of those double peanuts can still only hold 2 electrons. But if I have 5 d orbitals per energy level, and each of those 5 can contain 2 electrons maximum, we have a max of 10 d electrons per energy level. Well, now to our final orbital that we know of right now. It's being surmised that when we get to even bigger elements beyond 118 that we know right now, that there will be even more orbitals based on the pattern that we see, and you'll see that as we go through this. But the final one we're talking about and that we know of right now is the f orbital. And the f orbital is like 4 peanuts. So again, D for double, F for 4 peanuts. This is just my way of remembering it. Now, you're going to see some really bad art here, so I apologize ahead of time. So there's a double peanut, but if you look in perspective, it's like one double peanut in front of another double peanut. So those little arcs are trying to show you depth. And again, when I come back and I'll show you the real models, you're like, that's not at all what I envisioned, and I'm just a bad artist, so be kind. But at this point, you should all be able to figure out that 1s, 3 p's, 5 d's, 1, 3, 5. Next logical number would be 7. There are 7 f orbitals per energy level. And of course, again, seeing the pattern, we just take the number of energy level or orbitals per energy level, double that to find the maximum number of those types of electrons. So there's a max of 14 f electrons per energy level. So I hope you guys are looking at this and asking yourselves as respectfully as you can, why do we care? Like, okay, this is pretty complicated. Why would I care about this? Well, the answer is, if you remember too the importance of the subatomic particles, protons identify the elements, neutrons hold the nucleus together, electrons are responsible for chemical reactions. Everything that we, that makes us be, and our bodies grow, and our ability to create things deals with chemical reactions. So if we're going to have any kind of knowledge about the world around us, we have to know how electrons behave. To know how they behave, we have to know how they exist in an atom first. So this is the importance behind what we're doing. We have to know where they're at and how they're behaving before we know how they're going to change and exchange with one another or share with one another. So the problem with this is it's actually complicated. It's not nice and neat like the Bohr models like maybe you guys saw in middle school or physical science, which is fine at that level, but now we're taking it to the chemistry 1 level and we didn't know a little bit more about this. So I'm going to draw for you chlorine. I'm going to draw for you a chlorine atom. So chlorine, I don't care what the mass is, but chlorine has 17 protons. And if it's an atom, it's neutral, so it has 17 electrons. So I'm going to draw a chlorine atom for you. Not using the Bohr model, but using the modern theory, these complicated shapes. So that tiny dot right there that you can barely see is the nucleus. So I'll just draw this. Don't worry about how I know this at some point, but there is an s orbital. That's a two-dimensional sphere, right? Circle. Then there's another s orbital a little bit farther away. That's the second energy level. Then at that second energy level, we've got a p orbital, and another p orbital, and another p orbital. And then we've got another s orbital. And then we've got another p orbital, and another p orbital, and another p orbital. And this isn't my drawing that's bad. I mean, yes, it is, but this is what a chlorine atom would look like. And I haven't even gotten to the D's and the F's yet. So I'm hoping you guys are looking at that and saying, no way, I am not going to draw those. You can't make me, Mr. Engel. Good. I hope you're saying that, because I'm not going to make you draw that. There's got to be a better way, because if you look at that, even if someone's a really good artist, you would not be able to say, hey, that's chlorine. So there has to be a better way. Now, the better way, it involves some symbols. So be mindful of that. As we're looking at that better way of talking about what an atom looks like in terms of the electrons, this is the alternative, what I just drew in purple, and we don't want to do that. So the next thing I'm going to write down for you is called the order of filling diagram. Or the proper word for it is the Aufbau diagram. But I won't test you on the term Aufbau. So order of filling diagram. This is exactly what it sounds like. It's a diagram that tells you the order in which the electrons fill the atom. How do we know this? Experiments. This is what has been experimentally determined. It is not something that people just made up, like, oh, hey, we want this to happen, we're just going to say it's these numbers. This is the way that it goes. So a lot of experiments had to be done to determine, hey, where do those electrons go, in what order they go in. And as I had said earlier, things in nature prefer lower energy states. The elements fill up with their electrons the lowest energies possible. Note, I didn't say lowest energy level possible, the lowest energy. So there's two things that affect the energy of an electron. The energy level, distance from the nucleus, like 100-meter dash versus 200, and the level of complexity. Which course is harder? Chemistry or another course that's probably not as hard. So it's two things that affect the energy of the electron. Yes, the energy level, but also the orbital. So here is how we write that out. So my advice would be to watch this whole thing and then to very neatly put this into your notes. When I'm doing this in class, I tell students, put your pencils down. So I would encourage you guys to do that. Wait till the whole diagram is filled in and it's explained, and then you can go back and copy it down, because it has to be aligned neatly. If you're not a neat writer, you really need to take some time and do this one very neatly, otherwise you're going to be out of luck. So I'm going to write a coefficient. That coefficient represents the energy level. So I will write that down. The S, I hope is obvious to you, represents what orbital it is, the S orbital. And then we use a superscript. We don't call those powers or exponents because that means something mathematically. This is just a superscript, a number that's written higher. The number that's written higher in the Aufbau diagram is the maximum number of electrons that can fit in those orbitals at that energy level. So if it was just in that orbital, it would be 2, 2, 2, 2, 2, 2, 2. But it's in that number of that orbitals in each energy level. So I will write this in a different color so you guys can see. The coefficient is the energy level. That is the orbital. And that is the max number of electrons in those orbitals at that energy level. We will not always have the maximum number written down, but we will talk about that when I get back. So we have one S2. Well, like I said, we have other spherical orbitals, so we'll have a second energy level. So the first one, 1s2, is like the ping pong ball. 2s2 would be like the baseball. Right? It's a little bit bigger, hence the 2 in front. S, it's still the same shape. It's sphere, and it can hold a maximum of 2. 3s would be like the softball. 4s would be like the soccer ball. And then that's as far as my analogy went. But we actually go up to 7. There are 7 different spherical orbitals that the electrons can occupy in large atoms. So don't write this down yet. Wait till I'm done with all of it. Well, then the next orbital that we have are the p orbitals. P orbitals, it turns out, those shapes are even too complex to be in the first energy level. So we won't start with 1p because they're too complicated to be that close to the nucleus. So they start in the second energy level. Notice I'm lining up the 2p above the 2s. You'll see why. And there's a maximum of 6p electrons per energy level. Remember, 3 different p orbitals, 2 electrons in each of those orbitals. IB test question last year I'll share with you was, what's the maximum number of electrons that can fit in an orbital? And almost every student worldwide got that one wrong, they said, because students aren't reading carefully. The maximum number of electrons in any one orbital is 2. They're really testing, and I will really test your language on that. So we have 2p6, 3p6, 4p6, 5p6, 6p6, and 7p6. Now the next orbital is the d orbital. I hope you guys are kind of following along a pattern. 1s, 2p. Hey, d orbitals are too complicated to be in the first or the second energy level, so those would be in the third. 3d10, 4d10, 5d10, and 6d10. We actually don't need to go to 7d10 because there are no elements with electrons in that energy level and orbital yet. And then lastly, again, I hope you're following this. 1, 2, 3. The F's are going to start at the 4th energy level. So that's just the bare bones. Again, you can choose to copy that down now, but I would wait because the next thing I'm going to do is the actual order of the filling. These are just the different energy levels, the different orbitals, and then the maximum number of electrons in each of those. So things in nature prefer to stay in the lowest energy state. So it should be pretty clear that the lowest energy state for an electron is going to be the lowest energy level, 1, with the simplest orbital, s. So I'm going to draw this arrow on an angle like that. Again, wait, because then that's going to help you figure out how to draw these arrows. Well, then the next lowest energy level would be 2, and then the next simplest would be the 2s. So we've got 2s, 2p, 3s, 3p. Those are all the different types of orbitals and energy levels. The next lowest energy has to be the next lowest energy level and next lowest orbital. Now we've got an issue. We have electrons that can be in the second energy level, so close to the nucleus, and p, slightly more complicated orbital, so more energy there. Or we can have in the third energy level, a little bit farther away, a little bit more energy than the second energy level, but in the s orbital, less energy than a p orbital. So how do we know what happens? This is where the experimental conclusions need to be made. And we find out that like I didn't think part of it, what people have found out is that the 2p electrons have slightly less energy than 3s. So the arrow will still be on the same angle, parallel to the other ones, and go through 2p's before 3s's. And what that means is electrons have slightly less energy being closer to the nucleus in that p shape than they do a little bit farther away in an s shape. That had to be experimentally determined. Same thing with the 3p's and 4s's. Now if we look at the next row, or angle I guess, we've got 3, third energy level, so close to the nucleus, as opposed to 4 and 5, far away from the nucleus. And then we've got the d orbitals, very complicated, down to the p and the s, which aren't very complicated. It turns out the 3d's have slightly less energy than 4p's, which have slightly less energy than 5s electrons. And then we just fill in these arrows parallel to all the others. So that is the order of filling diagram. This is what you're going to want to carefully copy into your notes. Rest assured, you do not need to memorize this. You do need to understand how to use this. I will give you this on the test, actually. You will have this order filling diagram for the test. So you need to be able to use it. You don't have to memorize it, but if you do, things actually go quite a bit faster. So it's up to you. You do not have to memorize it. You have to be able to use it. Let me show you what this is going to do. So we will look at chlorine now. So I'll look at chlorine up here. Chlorine has 17 protons. If it's an atom, it has 17 electrons. So I have to place 17 electrons. So I will start here, 1s. So the first electrons will go in the first energy level, s orbital, and I have 17 electrons to place. I cannot write 17 up there because I can have a maximum of 2, as is shown in this diagram. So I can only put in as many electrons as that orbital can take maximum. So I'll put 1s2 is how you read that. I still have 15 more electrons. So you notice I started here, and then you go from the head of one arrow to the tail of the next. Don't actually dash this in because then that gets pretty confusing. After your first couple of times of using the off-bow diagram, things actually get you get pretty comfortable using those. So 1s2, now we can go to 2s. I have 15 electrons to place, but again, 1s2 down here can only have, 2s can only have 2 electrons in it. So I can only put a maximum of 2 there. Now we go into the next one, the start of the next arrow here, 2p6. It's good to keep track of how many electrons you've placed. I placed the max, 2 in this, 2 here, and 6. So 2 plus 2 plus 6. I'm adding up their superscripts right there. I have 10. So far I've placed 10 of the 17 electrons. So after 2p6, I just follow this arrow, and I go to 3s2. So that is 12 electrons placed. After 3s2, I go to the next arrow, and I have 3p, but I can't write 3p6 because if I put 3p6 there, I'd have 18 electrons placed. Chlorine atoms only have 17 electrons, so I say 3p5, indicating there are, in this chlorine atom, only 5 electrons placed into that energy level of 3 and orbital type of p, as opposed to the off-by diagram, which we give you having the maximum number possible. You can have less than the maximum. That's okay. So this is the electron configuration. It's called electron configuration. So configuration is setup. So it's the setup of the electrons in an atom. Now that might look ugly to you and seem a little confusing, and I would agree. It's the first electron configuration you've probably ever seen. If not, that's surprising. But keep in mind, going back to the last slide, that's the alternative in purple here. We don't want to draw what's in purple. And again, that was only 17 electrons. What if I asked you to do uranium's electron configuration with 92? That's going to be an utter mess. And if it's not neat and I can't figure it out, too bad. Whereas here, we can just represent this with letters and numbers for an easier way of seeing where that is. And this is going to become very, very, very important, like I said, because electrons are chemistry. If we don't have the electrons, we don't have a chemistry. If we don't know what's going on with the electrons, we don't know what's going to happen. And in chemistry, we really like to know what's going to happen. We like to be able to predict what's going to happen, knowing characteristics of each of these elements and compounds we'll be studying. So that is electron configurations. Keys to take away, clearly going backwards, using the order filling diagram here on this slide to be able to do an electron configuration like chlorines right there, right, to be able to do that. So that's one key takeaway. Another key takeaway from another slide would be the terminology energies and orbitals. Also, nature prefers things in lower energy state, and that the energy level and orbital both contribute to the energy of the electron. If you get that, those two things, and then also can memorize the S, P, D, and F, you will be very solid in terms of going forward from here.